So once again, I say good afternoon and welcome to the facilitation week, which is the seventh weeks on Physics 313, which is mathematical method for physicists. So we have this week and next week to round up the classes, and I believe the examination timetable is out already. So last week we tried to look at complex integral, which we tried to see how to understand what complex integral is and how to solve some problem related to complex integral. So this week and next week, we shall be looking at residual theorem. So what are the things we are likely to be discussing? We shall be discussing the concept of residual theorem and also try to see how to use residual theorem to evaluate integrals. Then by next week, we shall be looking at the application of the residual integration method to several singular points. So if you have any question, you can ask me on what we have discussed so far before we proceed with what we're expected to do this week. Any questions? Okay. So in the absence of no questions, so let's go straight to what we're expected to discuss this week. So like I said some minutes ago, we are to be looking at residual theorem. So the question is that what is residual theorem? So residual theorem is also called Cauchy residual theorem. So in complex analysis, and this is a powerful tool that is used to evaluate integrals of analytical functions that occur within over a closed course and can be used to compute real integral as well. It generalizes the Cauchy integral theorem and Cauchy integral formula from a geometrical perspective. It is a special case of the generalized Stokes theorem. Now, the main content is residual theorem. Suppose U is a simple connected open subset of the complex plane, and we have A1 up to AN are finitely many points of U, and F is a function which is defined and holomorphic on U as a subset of this if gamma is a rectifiable curve in U which bounds the boundaries A but does not meet any and whose start point equals its end point. So we can write that a closed integral, because if you look at this now, this integral with circle inside is called a closed integral over a gamma point of fz dz can be written like this as 2 pi I summation k is equals to 1 to n, then I gamma ak, then residual z. So if gamma is a positively oriented Jordan curve, then the term here, this one is equals to 1. So we left with residual f of k. So we now have 2 pi res f and k. So here, res f and k denote the residual of f at point k. And I this is the winding numbers of the curve gamma about the point ak. So all these are stories, but let's look at it critically in in a form that will be giving us an idea. Let's look at an example. We said example, the integral, that is this integration from negative infinity to positive infinity of EITS over s squared plus 1 dx. This is an integral now. So we have it like this. So the question is, how do we solve this? So it's a probability theorem when calculating the characteristic function of the Cauchy distribution. So it resists the techniques of elementary calculus, but can be evaluated by expressing it as a limit of contour integrals. Now, suppose t is greater than 0 and define the contour C that goes along the real line from negative A to positive A. Then the counterclockwise along a semicircle center at O from A to minus A. So now that is, we move from negative to positive and also from positive to negative. Take A to be greater than 1 so that the imaginary unit I is enclosed within the curve. So the contour integral is now this now. So this now, which is a contour integral of f z, dz is equals to this. What happened here is that they've replaced where you see x with z because we are moving to a residual function now. So we now have EITZ over Z square plus 1 over a contour. You see in this expression now, we've moved away from negative infinity to positive infinity of this S now to the Z. So you can see. So we have technically transformed that function to this. What we just did, I just replace X with Z and replace this X with the Z. Then the integrals now from negative to positive will now be over a contour. So since exponential itz is an entire function having no singularity at any point in the complex plane, this function has singularity only where the denominator z plus 1 is 0. Since z plus 1, z square plus 1 is equals to z plus I into z plus minus I. That happens only when z is equals to I and when z is equals to minus I. So only one of these points is in the region bounded by this contour, because so what I'm trying to say is that you can try to simplify this into a complex form. If you are doing that, you just split this z squared plus 1 using algebra function, that when you have a squared plus a plus a squared plus b squared, you can write it as a plus b, a minus b. So this is what they have used here. And by the time you open this, you get this back. So now they replace the whole of this now with this expression. Then the factor 2i out. By the time you do the expansion, you see that this is just like the factor that they brought out of that analysis. So we now have the whole of this. So this implies that so the residual f of z at z is equals to I is, if your z is equals to I now, if you put z is equals to I here, z is equals to I, then you now have I minus I. The whole of this goes to 0. If you put z is equals to I here, I plus I, this will give you 2I. Then it will now be 2I times 2I. That will give you 4I squared. And I squared is equals to minus 1. Then that cancels the negative here. So we now have ordinary 2 here. So we now say that this residual f of z is equals to exponential minus t over 2I. So according to residual theorem, then we have integral of this to equals to 2 pi, and the residual is equals to 2 pi exponential minus t over 2I, which is equals to this. And that is how this concept is being looked into. Now let's look at a more robust example. It says show that integral from negative infinity to positive infinity of cos xx over k squared plus s squared dx is equals to pi k exponential kx. So the whole of this expression now is equal to that when s is greater than 0 or k is greater than 0. Now look at the solution. Say, in fact, exponential x I x z over k squared plus s squared has only one pole in the upper plane, namely as a simple pole, that is z is equal to ik. So, and from 4, we obtain that is there is an expression here in equation 4. Let me see where that function is. It's not here. It's not labeled there. So we try to simplify this into this function. So we cannot say that the integral from negative of this, of the whole of this dx is equal to 2 pi this, which is equal to this, just like a kind of an assumption. So what has happened here is that we have tried to express this, which is an Euler's formula, in this format, cos x plus I sine xi. So this yields the above result. Any question? Any question? Okay. So now,
I'm having a
that is
question,
just a
sir.
kind of an introduction. You have a question, Isaiah?
Hello, sir. Hello,
Yeah,
sir. Yes, sir. Now, serious.
I'm listening to
Yeah,
you.
yeah, you need to slow down a bit because it seems you're too fast. Sorry. That's
Okay, no
just my
problem. I
observation.
understand.
Thank you, sir.
Okay, you're welcome. So now, so let's look at type of real improper integers. So another kind of improper integer is a definite integer. So in this case, if you have integral from a to b of f of x dx, so whose integral becomes infinite at a point a in the interval of integration. That is, like what we did in the first week of the lecture when we look at the limit. So the limit of x tends to a now of absolute f of x is equals to infinity. That's an assumption. So then the integral means if you have integration of a to b, that is the boundary, which we call the definite integral of f of x dx. So we can split this into this. That is the limiting of tau tends to a. So now our a now, which is the first point, going to a minus tau f of s dx, that we are trying to split the function into two different quantity and later add them together to give us the whole function. So it now equals to, that is plus the limit of tau tends to 0, a plus this to b of f x dx. Just like you have uh, a line that move from point A to point B, but you don't want to measure it directly, but you want to measure it in between. So you can divide it into two. So okay, let's measure from A to point C in between the A and B. So when you measure from A to C, you record it. You measure from C to B, you record them. You can later add them together. That's a kind of a layman explanation of what they have done here. So we are tau and this approaches zero indefinitely. And through positive values, it may happen that neither of these limits exist. That is, it happens that if you have a positive value, none of this limit that we are looking at exists. And if that happens, the whole of tau and this function tends to zero indefinitely. So, but if they if you now have this kind of things, you can say that this is called the Cauchy principal value of the integral, and it's written as PV integral of a to b of f of x dz. So I think the best thing is to look at an example to actually understand what we are trying to say there. So if we have integral from is 0 to infinity of sine s over x dx is equals to pi over 2. So this is the limit of sine integration of x tends to infinity. So the solution is that we do not consider sine z over z because this function does not behave stably at infinite. We consider exponential i z over z, which has a simple pole as z is equals to 0. That is, for this expression to equals to 0, z must equals to 0. That's the meaning of as z is equals to 0. So we integrate around the contour in figure below. Since this expression is analytic inside and on C, Cauchy integral theorem gives that the closed integral of this, the z is equals to 0. Now what they have done here is that this expression sine x, they have tried to express it as z in a complex format. And we know that exponential iz, which is Euler's formula, we can write it as a function of cos z plus I sine z. So that's why they are trying to say that we can transform this to this and later assume that it has a simple pole as z is equals to 0. So if you apply that on the problem, so we have this. So we prove that the value of the integral over the large semi-cycle C1 approaches R as approaches R as approaching infinite. That is, C1 approaches R as R also is approaching infinite. So when we set Z to equal to R exponential I theta dz, we now have I R this, and therefore the absolute value of this now, this expression, is now equals to, it's now equals to 0 to pi, because we have moved in time of angle now. So from 0 to pi, then less than or equals to this. So where z is equals to r exponential I theta. So the integrand on the right, which is this, is now equals to exponential minus r sine theta. I think we have to stop here so that we can actually try to look at it critically to understand the concept. So Nasri, do you have any questions?
No, sir. Go ahead.
Okay, fine. I think we have to stop here for today so that we complete everything next week. So do you have access to all the lectures I've uploaded in the last 6 weeks? Have you checked them on the course
I've gone
portal?
through all of them.
Not all of them,
Yes, sir.
but all of them are there
Yes, sir.
already, you know?
I've gone through. I've gone through them. I've gone through them.
Okay, fine. So that's good. So we stop this lecture here today, so we can continue next week to round up. And if you have any questions, so we look at it together next week before your exam.